I want to talk to you today about transformers, and I assume you've heard about transformers already. They've been used to quite a few tasks in the last year, so I'll go quickly over what transformers are and how they are used currently, and then later I will highlight a few problems that we know transformers have, and talk about some solutions that we've developed to some of these problems. And I leave some time in the end to start thinking, like, how far can we push these models? Do we need totally new models? What are the remaining problems? So, and I hope, like, if you have questions, please post them on chat. I will try to organize it to answer them. So let's go. Transformers. Transformers were introduced in 2017, and long time ago, meaning in 2015 or 16, which seems in machine learning terms like a really long time ago, people were using these networks called RNNs to do tasks that transformers do these days. And RNNs work as follows. Say you want to do machine translation, and machine translation will be like the running example, because this was the problem that everyone was focusing on at that time. That was the original problem that transformers were meant to solve. So if you have a sentence that you're about to translate, and say it starts in Chinese, and you want to translate it into English, then your RNN would read some embedding of every token step by step, and in Chinese the tokens may be just single characters. And in every step of reading the token, the RNN would make a state update, right? So the weights of the network are the same for every state update, but it needs to sequentially run through every token of the input. And then at the output, it will start generating the English sentence. And again, it will run step by step on every output of the English sentence. So that is a good idea, and it worked. It gave reasonable translations, but it's a little bit slow because of this very sequential nature. So it needs to run at every token, and before you run the next token, you need to wait for all the previous tokens to have completed, which is not computationally demanding, but it is slow on most modern hardware, like GPUs and now TPUs. So this sequential nature made RNN slow, and was one of the main motivations for Transformer, was to speed this up. But what hides behind this sequential nature, and I think turned out in time to be even more important than speed, is how the gradients propagate. So even before transformers, people knew about the attention mechanism, which here is depicted in the middle. And the attention was like something that people called alignment in NLP for many, many decades before, which is like, how would you align the English words with the Chinese words that come in the input? And the alignment is just a soft mask that says, well, for this word, maybe these two are the most relevant. And in machine learning, it's a softmax over weights that every decoder token assigns to every encoder token. So this encoder-decoder attention has been used. It was known that it improves translation quality, especially for longer sentences. And the reason it especially improves things when sentences get long is that attention allows you to propagate gradients in one hop, right? Because it's a mask. So from this word, say power, it propagates gradients to all input tokens that would correspond to it in one jump. While if you go the route of the RNN, you need to go many steps through a state update, and the state update contains a nonlinearity. And of course, gradients in RNNs, there were these things called long short-term memory networks, LSTMs. They were designed to improve gradient propagation in long sequences, but the lengths they can reach are still limited. So maybe you can do 100 words, which is okay for sentence-to-sentence translation, but you would not be able to do really long sequences. And in hindsight, the transformer architecture has improved that considerably and opened many new avenues of use. So we'll get to that in a moment. But if you look at translation, the moment RNNs were introduced into it, you could think, okay, how good should you do translation with neural networks at all, right? Because before neural networks, there was this thing that I call PBMT here, phrase-based machine translation, which was just a system a bit hand-designed to learn a probabilistic grammar, maybe with these alignments, and Google Translate ran this system, and it was not that bad. So if you score every translation from 1 to 6, 6 being perfect and 1 being totally bad, then these were like the average scores on some test set for the phrase-based machine translation. So you can see Chinese to English was fairly bad at 3.7, but even human translators wouldn't get 5 there, while Spanish and English is like the best language pair you can get, so it was much better. And the GNMT is the first production system based on LSTMs that was machine learned and introduced in Google Translate. And you can see that the relative improvement between the earlier system and already the RNNs was huge. The gap to human translators was cut dramatically. So it's not like these RNNs did not work. To the contrary, they worked amazingly, but they were hard to train, they were slow, and they could only do sentence level data. So in 2017, to help mostly with speed, I think that was the main motivation, we worked on Transformer. And the Transformer is a network that does not do recurrence in any form during training. It just does attention, and when it is supposed to generate, it does self-attention. So what does that mean? Say you have a sentence at the beginning, like I arrived at the airport or something. And so we'll embed this sentence and add some positional encoding. And then every token will attend to every other token. In this animated picture, these are the flowing lines. It means the tokens are attending to everything else. And then there'll be a feed-forward layer that is per token, so it's extremely parallel, right? It all happens at the same time, but the attention matrix, since every token attends to every token, is squared in the length of the sentence. So this is a problem that we'll get back to in a moment. And when you start generating the output sentence, there'll be self-attention as well, but this self-attention needs to be masked. So a token needs to only attend to the tokens that come before, well, because it will be generated, so it is necessary to not see the future, right? Because in the generation order, it doesn't exist yet. But in training, where you put the golden truth, it's already there. So you can do this as a network that is a purely feed-forward, non-recurrent network on training. And that brings huge improvements in speed. So you can see training cost on the right side here. And the training cost of a transformer is an order of magnitude or 2 orders of magnitude less than a comparable RNN. While, and that was a little bit of a surprise, the performance becomes much higher. So this attention mechanism, which is very generic, it does not have much of any like inductive bias in itself. It gets you to very high numbers, and the blue scores, which I remember like 10 or 15 years ago, improving 1 or 2 blue on these benchmarks would be like good PhD. And with these models, you get an improvement of 3, 4, you tune them better. They get to levels that are only achievable by human translators before. So you get really good translations with models that are actually not very expensive to train. So that was the transformers. And when looking at the transformers a little bit more in detail, one interesting thing that you can start to see is that the attention heads, if you see what the tokens are attending, they start to have some really interesting semantic properties. So for example, coreference resolution is the task of saying, like, if you have a pronoun like it, what does it refer to? And if you think of the sentence, the animal didn't cross the street because it was too tired, the it could in principle refer to the animal or the street. And if you have a sentence, the animal didn't cross the street because it was too wide, then the it is the street, right? While if it's tired, then the it is the animal. And you can see in the attention patterns that in some head of some attention of some layer, if you train the model long enough, and also not in all training runs, so this needs to be taken with a grain of salt. But you can start seeing that indeed the attention heads attend to possible coreferences, and they start resolving it, meaning they attend more to words that actually would be the coreference. So this is very interesting from an NLP point of view, that you can start translating sentences that have these ambiguities, because to resolve these, to translate a sentence into French from English, for example, you really need to resolve the coreference to know whether, for example, it's a masculine or feminine word. So there were no models before that would manage to do a reasonable job on it. And with transformers, we've started seeing that this works. So it's not just that transformers can translate, like in the blue score setting, they really start showing signs of better semantic understanding. And okay, so that was translation. Transformers can do amazingly on translation. That's great. But how about other tasks? So there was this benchmark called GLUE, which is a set of different NLP tasks in like reasoning and entailment. It's a bunch of tasks, and the measure is like the average score on all of these tasks. And even after transformers, people were like, okay, but this is really hard to do. This was meant to not be easy for machines. And it turned out that a model called BERT, which is just the encoder part of the transformer, but trained on a special masked loss. So you just remove a few words and try to predict them. It got like much better than anything that came before. And then for future improvements to these models, managed to outbeat humans on these tasks too. So this transformer paradigm, plus a lot of work and engineering put into it, plus a lot of pre-training on a large corpus. So you make this masked loss, take a large corpus, train. And these models get really good at tasks that we thought earlier need human understanding of language. And on the other hand, if instead of the encoder, you just take the decoder of the transformer, it turns out you can start generating really long text. So one experiment we did, we gathered, say, 20 Google searches for a query, but excluding Wikipedia, and tried to generate the Wikipedia page from that. And it turned out transformers do a reasonable job, actually. They can generate then from just Google searches quite reasonable summaries of what is being done. And another thing, though, that is easy to observe is that to make this work well, you need quite large models. So if you take a model with, say, 20 million parameters, which is quite small by today's standards, and you try to do such a kind of generation, then it will put some sentences, but they'll not be very sensible. Like Pescadores is named after the Lord of the University of the Gravity of Drama. I mean, it makes no sense, right? It's a sentence, it has words, but it's not clear. You take a 10 times larger model, and it starts making way more sense. And it starts even knowing, like, what people's political affiliations are. It starts showing some world knowledge. And then you go even higher. So GPT-2 is a model with a bit over 1 billion parameters. And these models start generating text that's good enough that The Economist made an interview with the model in the New Year's edition. And the model only did the answers, and I think they were a little selected, but you see it. It generates reasonable answers to the questions, and reasonably enough to publish in a newspaper. And so the models start at this billion parameter scale doing interesting things, just pre-training on the internet. And then you go up, so GPT-3 is a model with 170 billion parameters. And there is something amazing when you start doing this, because the model can generate whole stories. So GPT-3 is used in a game, and you can start seeing, oh, you arrive at a small wooden store with sheet music in the window. The door is locked, so you knock. Music stops. What's happening? It can generate not just like one answer, not a few sentences, but a story that goes on and on and on. And maybe you say, like, you go inside, and then it generates a continuation to this. And you know, there are people in this world, and other creatures, and there's a kingdom and a queen. So it starts to be really interesting, and it also shows this behavior without, like, you can start to have it solve tasks without training. You can just say translate from English to French and give it a few examples, like sea otter, peppermint, and then you ask for another example, and it will just work, because it's been pre-trained on so much data, and it's so large that it has memorized all of it, that it can start solving tasks few shot. And the thing that's important here is that, to some extent, the size is important. So a model with like GPT-2, just 1.3 billion parameters, shows very bad accuracy on these few shot tasks. While when you jump 100 times in size, the accuracy gets amazing. Now, currently, we know you don't really need to jump 100 times in size. If you have the right data, if you format the data in the correct way, like do prompt data, gather a data set, you can get a similar effect with much smaller model. But if you're just training on the internet, the size really helps you. Okay, so the models do amazing things with text. Can they do things with other things, with images, for example? Yes. So if you train a transformer model that just takes text as input and generates an image for the text, and the image is generated in this very strange way that you can imagine it's like pixel by pixel from left to the right. It's not actually pixel level. It's encoded in discrete vectors that have like small patches, but they're almost like pixels in lower resolution. It can, you know, it will generate you like a baby daikon radish in a tutu walking a dog, and that was certainly not in the training data, right? So it's understood a little bit how babies look, how radishes look, how dogs look, what it means to walk a dog, at least in means in terms of look at an image. And you can say, okay, an armchair in the shape of an avocado. Do you get it? You can say a storefront that has the word OpenAI written on it, or some other word. It's not very good with words, but it makes them, right? So it has totally, without any clear training data, just from images on the internet, learned about letters and what are storefronts. And more recently, you can do the same to generate code. So you can start with a definition of a function, maybe some comment, and just ask the model, hey, could you please get me the code? And it does. It will just generate a completion that's a very reasonable code. Now, very reasonable doesn't always mean correct. It's not always quite exactly what you need, but it's a very good start towards, you know, if you look at it, edit it, it may be much easier than writing it yourself. Okay, so transformers are great in many domains. So what are the problems? Well, one problem that we've already mentioned is that the best transformers are really big models, and running a 100 billion parameter model is tough. The other problem is, well, this attention, as we said, every token attends every other token. And that is the source of speed and good gradients. But it's a quadratic matrix in terms of the length of the input. So if you do single sentence, the length of the input is maybe 60 tokens, maybe 20. It's not a problem. Even if you get to 1,000 by 1,000, this can be handled. But if you get to like 10,000 length, so you know you want to write a book or a longer article, the ending of the article may depend on the beginning, so you should have this in the whole context. But the transformer would be so slow that you wouldn't be able to train it, and just generally miserable on things of this length. So the problems we have is, this is illustrated here. If you take a bird and try to increase the sequence length and have a 12 gigabyte GPU with this version of TensorFlow, the maximum batch size you'll be able to train on will be 0 because it just won't fit. And you can make the code a bit better, so maybe now it's slightly larger, but the fundamental problem is this quadratic dependence on sequence length. And the other problem is you want to have 100 billion parameters, and that really also doesn't fit in memory. So if we do nothing about these problems, then in the near future, it would be impossible to fine-tune state-of-the-art models without being at Google or OpenAI, where there is a whole data center dedicated to one model and the team doing nothing but fine-tuning it. So that's a little bit sad, because these models are really good, and it would be nice if we could have them at home, work with them, research them, move on. So the thing I want to highlight is that there are research ideas that are starting to work, where we believe that transformers can be adapted to run on today's hardware over really long lengths, up to say even 1 million tokens at a time. And we believe we can make even large models run reasonably efficiently, at least at inference, without these huge hardware resources. Okay, so how can we do that? And this is like a number of techniques that we present, and others have introduced even more. So I'll go quickly over those. But I think the highlight that I want you to remember is that there are actual solutions that work. So we, whether this is exactly this technique or some new technique that will come this year, it's less important than to understand that both these problems, so both the long context problem and the scaling of large parameters problem, actually can be solved. Okay, so how can they be solved? Well, let's start with memory efficiency. So if you want to run a transformer model on something that has 1 million tokens, right? Then here's your problem. A D model, even of a small model, say, is 512. On a larger model, it's 1,000. So just this tensor after embedding, right? You've embedded your tokens. This is the first layer. You haven't done any work yet. It's already about 2 gigabytes in memory. And then you have a number of layers. And for backprop, you need to save these 2 gigabytes after every layer. So even with 12 layers, which is not a huge model, you already have 50 gigabytes. So you've already run out of your GPU memory by far. And that's without counting anything in the layers, right? These are just the intermediate activations. So that we can't do this. We can't store these activations all the time. So one method for this is to recompute them, but then you need to start thinking when you recompute and so on. And an easy alternative to recomputing is something called reversible nets. So a transformer is a residual network. It always adds the activation to the next layer. And in a reversible net, you have 2 copies, and you only run a layer from the left copy to the right and from the right copy to the left, and you add the layers that were before. And the reason you do it like this is that this allows you to reverse the network running backwards. So not only can you compute the outputs from the inputs, but you can compute the inputs from the outputs. And that's actually just by running the same layers and reversing them. So in the case of transformer, the layer 1 is the attention and the layer 2 is the feed-forward block. And then, okay, so you have twice the activations in every layer, but you don't need to cache them. So 4 gigabytes is all you're using. So that's a nice saving. You can have a lot of layers and you're only expanding the memory for one layer, except for parameters. So does this work? Yes, you can make a transformer reversible and it gets the same performance on translation. Here it looks like slightly better, but it's probably just because it was tuned better. So, okay, So reversible transformers work, and they can save you a ton of memory. So now you can run a training step on a single GPU where you'd need a multi-GPU or a multi-machine setup to run this before. Great. Next, so time complexity. Well, the embeddings and the feed-forward layers of transformer are linear, right? If you have 1 million tokens, you still need to run 1 million embeddings, but this is parallelized on GPU. It's a lot to run, but it can be done. But how about attention? Well, attention it has this length squared dot product in it. So 1 million squared is something you will just never run, even in great hardware that comes in near future, because it's just too much. But you can start asking, what does this attention actually do? Because attention is a softmax over these activations. And in many cases, it's actually fairly sparse. So there are queries that are attending to keys, and a query should generally attend to not too many keys. Now, this is not always true, because sometimes there are very flat layers that also do like queries attend to. And these keys, by definition of attention, are the nearest neighbors to queries in the cosine distance. So can we compute nearest neighbors between a set of points fast? So here is an illustration of how you can do this with a very old technique called locality sensitive hashing. Imagine we're in 2D. Well, in transformers, we're in much higher dimension, but here it's just for illustrations, we're on a 2D plane, and you have a bunch of points. So you want to compute nearest neighbors from point to point, and to do that naively, as happens in the attention, you'd compute the distance between every pair of points. That's where the quadratic thing comes from, and then select from that. But what you can do instead is pick two random lines on the plane and only compute distances between things that lie on the same side of these lines. So you see, like on the left, you have these 3 points. You'll compute only these 3 by 3 distances, and indeed the nearest neighbor will with high probability be between these points that are on the same side of the line, because these are the points that lie close to each other. That's why it's called locality sensitive. Now, you can see this blue point close to the yellow ones, that it's not always correct, right? It's a probabilistic method that's probably correct, but it may have outliers. So to deal with that, you need to sometimes redraw new lines, because you draw them at random, and redo this. So can you apply this to attention? Yes, you can do this locality sensitive hashing on your queries. It's more convenient if queries and keys are the same, but that actually doesn't matter for transformer that much. You do this locality sensitive hashing, you sort by the hashes and attend only within these hashed buckets. And in this way, you can run attention on in time n log n, so you can actually run it on very long sequences, even of 1 million tokens. But since it's a probabilistic method, sometimes you need to redraw. So you need to have an attention layer that actually repeats these things a few times. And does it work? So we tested this on ImageNet, which is like, I think, 12,000 tokens or so. And the black line, which is the full attention, you can still run it on it, even though it's very slow. It's a little better than the locality sensitive hashing ones, but as you increase the number of hashes, you start getting there. And the speed, well, it grows linearly with the number of hashes. That's why you don't need too many of them. But the speed of the full attention, well, its complexity is quadratic. So with length, you'll still be much faster. Okay, so locality sensitive hashing is one solution to running attention on really long sequences. There are many other solutions, like routing transformers would pick a few important vectors and just attend to this. A performer is like more RNN-like approximation of attention. You can use multi-layer patterns. There is something like perceiver. You can also make the model hierarchical, so it can compress vectors one by one. This is to say there are many ways to do sparse attentions, but at least one we know that works. So this shows us transformers can actually, when properly modified to have an efficient attention layer, handle long sequences. So that's great because it opens the whole field of like, we can put a lot in the input and the model will process it and work. Okay, so how about the number of parameters, right? If we have a billion parameter model and we want to have more and more parameters, that's still very hard to run technically. And the parameters, like while the attention is quadratic in transformer, it has very few parameters. Most of the parameters are actually in the feed-forward layer. And the feed-forward layer is just a linear layer, a ReLU, and another linear layer. So we have an activation vector, which is of size D model, and we multiply it by this D model by DFF matrix. DFF is oftentimes, say, 4 times D model, sometimes it's even 8 times D model. So it's a larger number. We get this larger vector, run ReLU on it, and then multiply it back to be of size D model. So we have 2 matrices of size D model by DFF. That's where most of the parameters lie. Now, think of this ReLU that you run in the middle. Like some of these numbers will be zeros, or quite a lot, because ReLU, every number that's negative, it will become a 0 after ReLU. Now, if you knew beforehand which of them will be zeros, then you could save yourself retrieving all the parameters from memory that's in the matrix above these zeros, right? Because you don't need to know what this will be. You can, if it's 0, you wouldn't have to retrieve this at all. And the same for the other matrix, right? All the columns that are 0, they're not needed. We retrieve them from memory, multiply by this matrix, but it all disappears. So that's a place where we could have a lot of savings. So here is an idea. Let's have a very small controller, like D model by, say, something low rank, like 32, something really small, that will predict which of the things will be zeros. And it doesn't need to be perfect, but we want it to predict a fair bit of them to be zeros. What is a fair bit? Well, at least, say, 1 in 64 or 1 in 32. And once it does it, we will not retrieve these parameters. We'll only retrieve the non-zero ones. So that turns out to work really well. And so that's the part of parameters that are in the feed-forward block. And there is also a way to handle the parameters that are in the QKV layers in attention. I'll not go into this, but it can be done too. So if you do use both of these tricks, you move all parameters into this sparsity, you can get huge improvements in decoding speed. So we have a model we call Terraformer that's about 30 times faster in decoding with these things than a comparable model would be. And the extremely interesting thing is that even though you have these sparsity controllers, so you're guaranteeing that there'll be a lot of zeros in the ReLUs, you may say, will this sparsity hurt my training? Will the perplexity be worse? And the answer is no. It turns out you can scale transformers just by having sparsity, and they behave very similarly to non-sparse models with the same amount of parameters. So we can actually, instead of putting larger and larger parameters that are activated on every forward pass, we have all these parameters, but we only retrieve from memory a small subset of that. And that gives huge speedups at decoding. And to get speedups on training, there is some additional work to be done because you need to handle batches. But with large models, it's often batch size 1 anyway. So that's an ongoing work, how to bring these speedups to training. Okay, so how does it look? I think the transformer future looks quite promising because we can run transformers efficiently on really long sequences, and we can make decoding and maybe even training really fast thanks to sparsity. And with the memory savings that you get from reversibility, you could even fine-tune these models on a single GPU. So we can have big transformers with large contexts running on very moderate hardware, and that's great. On the other hand, like the thing that happens in parallel to all this research is improvements in infrastructure. So there is the transformer package from Hugging Face, and Hugging Face as a company now allows you to run online a ton of transformer models, and even like 2 billion, 3 billion parameter models you can just run in the browser. They will host them for you. So everything has become much more accessible too. On the OpenAI playground, you can run the Da Vinci model, which is GPT-3 sized, so 100 billion model. You can just go there, type a text, see for yourself that it solves your tasks without any training even. So I find it very beautiful that that things can be run online without having any hardware on your own. Now, how good are these models? So we know that large transformers can do zero-shot learning. They can solve language tasks, but can they for example, code? Can they write code which is not trivial? Well, this is something we tried to explore with the Codex models. And if you ask them, you give them simple programming exercises. Simple meaning they don't require a huge amount of thinking on like algorithmic expertise, but they do require writing code that's not exactly stated, right? And you start measuring what is the pass of these models. Then the important thing is, like, as you make them better, they can pass more and more tests. So that's nice. The other interesting thing is if you sample more from these models. So instead of getting just one sample, you get 100 samples. Then you get even higher rates, right? So in like just one sample passes on average at 30%, but 100 samples will pass 70%. So if you have unit tests to check the correctness of your code, then you can pass way more, right? You can just generate and get better results. And so there is a data set called apps, which is much harder than these problems. Like competition level problems in apps are actual problems from programming competitions where you need some algorithmic expertise. And previously, like, models were not passing this, but we see that models that are really trained on a lot of code with a lot of compute and with some filtering, like you allow 3 unit tests or so, they start passing a small percentage of these tasks. But now, as we improve these models, this is getting higher. So these are real tasks when it's not obvious from the description what the solution should be, but still the model is starting to manage to write these solutions. So can transformers do everything? Well, not really. So here is a work that's appeared very recently. It was submitted to iClear, so I don't even know the authors, but it's a work on, it's a simple task to add numbers. You get the numbers as a sequence of digit, long addition, and you want the transformer to add them. So you'd think, okay, there are these transformers, they can do images, text, language, they should be able to do everything. But here is this trivial task that you learn at school, and they can't do this, right? They can code you a calculator, but they can't add these numbers on their own. Like if the baseline, the standard transformer is the blue line, and you see that you can make them super big, it's still at 0. There's no progress at all. But if you give them a lesson, right? If you give them this scratch pad where in the middle you'd show them how these operations are actually performed, as you and me learn at school, right? Then the models start getting it, And they start getting how to do this for more digits too. So this is out of distribution accuracy, the plot on the right. And the one with the scratch pad, you can also see that the model needs to be of a certain size. It's still, the small models are still very close to 0, but then it goes up and it gets actually very good accuracy. So you can clearly see that transformer on its own can't do much, but if you give it these lessons that we do learn too, and ask it to actually generate the thinking, then it works. And there are papers recently that study transformers in more formal settings. So it seems like with this enough space in the middle of extra data, it should be able to emulate any Turing machine runs to solve very complicated problems. Now, this is still to be seen. This was blocked mostly because this adds a lot to the context length, right? You're having like a lot of text in the middle. So you need models like the efficient attention models that can handle large contexts. You can see for this plot also, it only starts working with larger models, right? So you need large models. You need models that have a long context. You need additional techniques like adding these scratches or maybe things that we haven't thought of yet. But with all of that, I think there is actually good hope that these updated transformers with long context, efficient scaling, fast decoding, and science of these reasoning things, they may go a long way, right? They may actually like write competition level code or generate images and videos that really make sense. So I do think there is still a long way transformers can go, but not just on their own. They need all these improvements. So let's keep working on them. And that's it on my side.
Thank you, Lukasz, very much for your amazing talk. And right now, let's move on to the questions and answers. So the first question, the most upvoted question was, when we are scaling the size of transformers, how much of that improvement is from deeper understanding of the language, actually, of the language structure, of grammar, and so on? And how much is it due to just memorizing a lot of combinations, and can we measure it?
I think it's very hard to measure accurately. What we know is that the models are becoming better on the tasks, right? This is the statement we know. Now, how exactly are they becoming better is a very tough question that many people are trying to research. And it seems to depend on a lot of details. So you can definitely train like smaller models on a bit better data or train longer and get the performance of a bigger model up to a level. And then there are other tasks and ways where it seems like the size really matters. So I feel like this is an area that needs more research. Like, why are they getting better? We don't really know, I would say. But we're trying, and it's because it's just so hard to know what it means to understand. Because it's like, I mean, understanding is really related to the world, right? And these models don't act in the world; they just produce text. So we're trying to inspect them in many ways and see, is it what they're producing reasonable? But in the end, it's just very hard to know. But there are many very smart ways of when people are trying to figure this out, and it's a very interesting question and area of research. It's just, I feel we're not yet there to really know.
So coming back to the idea of inspecting models and looking into them, there's a dynamically growing area of explainability and trying to interpretability, trying to understand what the models are trying to think inside of them. There are many techniques that are being proposed, and there are, of course, many more ways of hacking these techniques. So one of these ideas is to use attention as the explanation for the model prediction. So we're trying to explain the prediction of the model using attention, and we can like look at this quantitatively quantitatively it's a bit harder, but like looking at this qualitatively, it's just by looking at the prediction and saying, okay, this makes sense. And there are some publications, and there's people are divided across it. And what are your thoughts about it, especially in the context of MLP? That's
Well,
the question.
it's one of the simplest things you can do, right? Because you actually have, like, when you run the model forward, you have the attention weight, so you know where they're looking, and it's easy to plot it, and it sometimes shows you something interesting. But there were many publications also criticizing this way, because the attention, especially in large multi-layer models, multi-headed, gathers the information, and then the next layer can forget some of it. So it's not clear how far we should go in using this thing as a means of what is the model doing. And it seems like there is something in there, but you need to be really careful, because some things of that may be misleading. I think people have like now more convincing methods where you actually try to put the contribution of training examples into the gradients. But it's a very active field of research where I don't think there is an answer that would be like, do this and don't do that. It's like you try to look at many things and draw some weak conclusions, and then try to test and verify them in many ways. Because it's really hard, right? It's the big models, they do a lot of computation, and a lot can happen there. So it's sometimes hard to like say what is the main factor here. Well, it's 96 layers, and each of them contributes in some way, but yes.
Okay, I swapped with Franek because of some audio problems, but we can proceed with next questions. So yeah, I think that now we can focus on some questions about the limits of this approach. And we have interesting questions about the data sets. Do you think that we will hit the limitation of the size of the data sets that we need to gather in order to train such a huge models?
So it depends what you want to train them for. I mean, there is still a lot of language on the internet, and it seems pre-training on the internet helps with many tasks. So in the language domain, there is not that much limitation yet, but there is. I mean, if you want your transformer to do one particular thing really well, say, I don't know, write legal documents in Polish. Now, there are not that many legal documents in Polish on the internet, and that will probably not be enough to train a big model to do that really well. So I do feel like we're hitting data problems in specific tasks. Now, pre-training seems to help in a lot of that. So if you pre-train on all Polish on the internet and then fine-tune on that, that's a very reasonable method. But it will also reach its limits, right? So the question is like, could we make these models more data efficient? And there is, I mean, there's some of the old good works like Dropout, right? Dropout can be used in transformers. It works really well to help fine tune, especially on small data sets. There are things like SAM, which is different optimizer method. I was very excited. Recently, there was a paper called MEND about how you can change the model with just one example. Like you want to tell the Prime Minister of the UK is a different person than I think it is because something changed. And they actually have a method of modifying the gradients, because if you fine tune on one example, it will just memorize this, but any other query will still give the wrong answer. And on top of memorizing this, it may actually drop performance on everything else. So it's not a good idea to just train model too long on one example. But they have a learned way to modify the gradients where it actually survives and generalizes. So I think this is very exciting that there are ways where people come up with better methods of training on smaller data sets, or maybe fine-tuning rather than training, but that's for specific tasks that this is very important.
Mm-hmm. Okay, thank you. Yeah, there are some papers related, for example, to the thing that we can pre-train on completely different problem, and it still can help us to achieve some better metrics on our problems. And so yeah, the solutions like this could really be helpful. And yeah, we have also another questions about the limits, because during the lecture you mentioned that we should make further work on transformers, proceed with the next updates and upgrades and research in that direction. So the questions from the audience is, what do you think is the fundamental limit of transformer architecture, and will this approach lead to the AGI, or maybe not?
Well, it's a AGI is a not very well defined term, so everyone can think of different things. But I do think transformer models can work really well on a lot of tasks, and I think with all the new techniques, and especially with long context combined with large models and things like these scratch pads, they should be able to work on tasks like coding, where the problems get really harder. So there is some reasoning to be done there, and that's already very exciting to me. Now they can generate images, so they should be able to generate videos. The question starts to be, is this the best way? Because if the models are very expensive to run, it's not like currently, if I were to generate images, I would use a diffusion model, which could have a transformer inside, but it would not be the autoregressive decoder transformer model. Because it's like with DALL-E, you can see that a transformer can do this too, but it's really hard to train. It needs to be really large. While a diffusion model can see the whole context, the Gaussian noise for an image is very nice. So for some problems, there may be better models. Will there be better models for text? I'm very curious. There is diffusion models for text have shown some signs of life recently. There were a few papers. I'm very excited. Maybe they'll work. Maybe they'll work even better, and they could have a transformer inside them. But maybe there is something in text that just goes fundamentally left to right. That this autoregressivity, like generating an image pixel by pixel from the left to the right and from the top to the bottom, is not reasonable, right? No one draws images like that. While text we do write from start to beginning to some extent, maybe not very long pieces, but at least. So it remains to be seen, right? Whether it is, but at least for language and code, it may turn out that this is actually a solution that will stay. But maybe there will be like 10 times more efficient solutions. It's always exciting to watch and think of that.
That is the clue of the research, right? Okay, thank you very much. Also, we have a question related to focusing on one model. So on this conference yesterday, we had panel with Sarah Hooker, who is author of a paper, The Hardware Lottery, which describes the problem that sometimes we can focus on some area of the research too much. When we involve too many resources into one domain, and it's possibility that it was wrong idea to invest that time. And there is also one question related to exactly to that problem, because the question is, should we worry that focusing on the single model, the researcher may fail to look for the conceptually different but possibility better architecture?
Well, we should definitely study many things, right? We should study many architectures, but there is a flip side, and the flip side is machine learning is not just model architectures. In the past, model architectures used to be like extremely important, and I feel like transformer allows to flip the thing a little bit. So now when the model is fixed, it's just a transformer, then people start to study, okay, if I change my data, how will it modify? If I change the whole system, if I do RL, if I do something else with the whole outside of the model architecture, maybe this brings even better gains. So I think it's a nice thing to have this one model that you can really trust, that's well implemented everywhere, because you can do all the things around it that oftentimes turn out to be more important than, like, say, the scratchpad idea or diffusion models. These are ideas that can work with any architecture in the middle, and transformer, maybe once we make them work, it will turn out that there is a different architecture for them that's actually better. So yes, on the one hand, we should investigate other architectures, definitely. On the other hand, Transformer allows you to fix the architecture. It's implemented, by now you have it in all frameworks. You can trust that it will train and go beyond and investigate all the other things. So yeah, but I agree that there may be very interesting things in the architecture to change, and that I'm a big fan of something called simple recurrent units, SRUs, that can actually be combined with transformers, and yeah, it gives gains. It may not give gains that are it hasn't become famous, I guess, but it can improve transformers on tasks, and it's definitely worth investigating. The question though is a lot of times improving your data will give you much bigger gains than improving the architecture by now. So that's
Okay, thank you very much. I think that it's answered the question. And now we have the questions about semantic parsers. And do you think that NLP or NLU things like semantic parsers are still important, or big language models are enough nowadays?
Well, I started my work in machine learning with the in a semantic parsing group. And the semantic parsers always had the problem of who is using their output, because you output some logical thing, and every system downstream needs to use it, right? So it's very different than a language model, because a language model just generates you the answer, period, right? You never present the output of a semantic parser to user, right? You need another system that needs to do something with it. And it's that interface that is the problem, because the group that does the semantic parser needs to talk to the group that does the other thing, and they need to work together, and then you may not know who's responsible for a mistake, or where should it be. And so a big advantage of deep learning is that it's end to end, right? You have an input, all the data you have on input, and here is the output. And if the output is wrong, you ask someone to write the right output and train on it. And that's simply not achievable with the non-end to end. Semantic parsers are by definition not end to end, because the user is never supposed to look at the output of the semantic parser. I still think they're interesting and important for linguistics and for many domains, but in the production we're solving a task for the user, it is not clear how, the end-to-end approach is just much easier to practice and debug and correct.
And to explain.
Well,
okay.
Sometimes to explain. Sometimes it's hard to explain what these models do, but yes.
Okay, thank you. Okay, we have also questions about Alice Hay. How do you do the clustering in the locally sensitive hashing efficiently? In general, this is a NP-complete task, or you just ignore the clustering step?
Oh, so in locality sensitive hashing, you don't do clustering. You just, maybe I explained it wrong. You take a random hyperplanes, and you will only compare things that are on the same side of all hyperplanes. So where was it for 2D? Here. So you draw two random lines, and you call a cluster the things that lie on the same side of these lines. So here you'd have 4. You can call it clusters, but there is no clustering, right? It's just you're on the same side of these 2 lines. So your hash is actually the bits. Am I on the left or right of line 1? Am I on the left or right of line 2? And so on. And in higher dimensions, these are hyperplanes. So there is no clustering. You can call them clusters, but it's just random hyperplanes and being on the same side of it. And because it's so random, you sometimes need to redraw and take some other random lines and combine the results from a few of them.
Okay, thank you. I think that explains a lot. We have also questions, I think, kind of theoretical, but yeah. How far are we from the next breakthrough comparable to the introduction of transformer? Do you think that there is some clear direction in which we should proceed, or maybe somebody are working on currently?
Well, I mean, I think a lot of there's been a lot of work, right, and a lot of it is it would be fair to call it breakthroughs too, right? There's been a lot of great work going on. It's in machine learning, you never know whether it's a breakthrough or a trick until a few years later, I feel. I remember talking to Jeff Hinton, and a lot of people called dropout a trick, and for many years. But I think it's fair to say it's a breakthrough, and in some sense, attention is a trick of sorts too. It just turns out to work really well for many cases. So we'll just see. It may already be here, something that works really well, and it's just. I feel nowadays it's harder to just filter from all the things that are being done. But it's important to not just work on the architectures, but also to think like how it relates to data. And even if we have like this ton of data, like on the internet, there may not be enough data for the problem you care about. So people are starting to think, okay, how can we make models efficient, but not, we don't need to train a huge model from scratch efficiently because we can train it on all of the data, but we should fine tune efficiently. So I think things like the MEND paper, like these studies of data efficiency are definitely a very interesting direction that I would highly recommend. These scratchpad-like ideas are also like they increase the power of the model and its generalization, it seems. But there may also be additions to the architecture that will get similar effects. It's a really good thing back in Transformers age was the translation benchmark. Everyone knew, okay, this is the benchmark, you get better on it. It means your model is better. It's harder now because it's not a good benchmark anymore, right? We've gone too far in translation. You can't expect it to improve dramatically. Low resource translation maybe, but maybe there should be other benchmarks, right? And maybe the lack of a very clear one benchmark is a little harder, but I think there is still a lot of very interesting things